All right, it is noontime, so I'm going to get started. Oh, it's it's running out of battery right away. That's okay. It's because of the weekend. Blame it on the weekend. It's okay, I got it. So I don't know what you guys did over the weekend. I learned how to program on a mainframe computer over the weekend. So it was kind of exciting. But the technology that I used to do that was because I needed to figure out the instruction, not for myself, but for students who are mostly using Windows. But I got all of my tools set up on the Linux side. So I have QEMU, basically it's a virtualization machine, to run Windows. And then inside the emulator Windows, I ran the mainframe emulator that then ran the mainframe computer, which is it's called a System 370. I think it's from the early 70s also. So that was like double layer of emulation, and the whole thing worked just fine. And according to the timing, I think the emulator inside the emulator was still running, like at least 100 times faster than the original mainframe. So it's double emulation, and it's not even using the Intel emulation technology, because the instruction sets are entirely different. So it's really time-consuming kind of emulation. And I was learning COBOL. I'm sure some of you have in this generation, it will be grandparents who program in COBOL, and they will share those war stories with you, like how to program in COBOL. Okay, this mic is really directional when it's not supposed to be, but that means I cannot turn my head, because the moment I turn my head, it will change. Well, maybe, there you go. See, it changes. La. See, this is the optimal angle. I have to kind of keep doing this way. I can twist my torso like Batman, right? Huh? And I have lots of devices on my belt like Batman. Huh? If I'm Batman, who's Joker? All right, so what we'll do today is we're going to start to talk about relations. And it's an interesting topic. It doesn't seem like, it seems really theoretical, but at the very end, we'll start to understand why it is important to talk about the mathematical notation of a relation. So before we even get started, okay, I don't want you guys to feel that this is like super abstract. So I want to let you know that you have been using these since cisp440. Because comparison operators, like less than or equal to, those are all relations. They all relate a value to another value. Or to be more precisely, they all express whether a particular value relates to another value or not. Okay? So we have been using relations for a long time already. We just never took a look at relations the way we're going to do it in this class. So we're going to start with what is a relation. A relation technically is whether two elements of a set are related or not. Okay, so you can define a relation over a particular set. That's how we say, how we describe a relation. So what we'll do is we use the English sentence here and say we consider a relation R that is defined over a set X. So X can be any set. Okay, if you want to say, okay, I want this set only to have A, B, and C. Fine, not a problem. If you want to say, I want to look at the set of all natural numbers, that's fine too. Okay? So X is really just a set. And R is a relation that is defined over that particular set. So the first thing we know about the relation R that is defined as set X is R is a subset of X Cartesian product with X. Okay? But you guys would remember that a function is the same way. Okay? If I define a function where x and x are both the domain and the codomain, then the function is also a subset of the Cartesian product of x with itself. Okay, so what makes a relation different? So we move down a little bit. There's basically no relation to, there's no restriction to the subset R in this case. Okay, that is, because it's very directional, so if I turn my head just at the right place, it picked up the speaker, and that's why it has a lot of echo. So if I change it, maybe to twist more to this side, let's see if that helps. Okay. So from the notation perspective, the first thing we do is we can say x relates to y, and we express it like this: x and then the symbol for the relationship, for the relation, and then y. Then you go like, hey, this is how we write x is less than y, or x equals to y, or x is greater than y. That is because all of those comparison operators are relations. Okay, so from here on, whenever you see a less than, whenever you see a greater than, and so on, they are relations. Okay, we have been using that concept of relation for a while already. So this is kind of the infix notation of a relation, where the relation is, or the notation of the relation is between the values that we want to say, is there a relation between those two elements or not? So it is important to understand that this is Boolean, okay? X, R, Y is a Boolean value. It is either true that X does relate to Y using R, or it is false. X does not relate to Y using R. So you can define any number of relations over a particular set. Just like with integers, we have less than or equal to, we have equal to, we have greater than or equal to, and then we have, did I say not equal to? Okay, so we also have not equal to. So all of those are relations that we kind of use a lot in programming. Do we have any questions over the concept of relations? I understand that we haven't really talked about a lot of limitations or restrictions, because functions come with a lot of restrictions. Okay, in order for a subset of the Cartesian product of x and y to be a function, well, we have a lot of restrictions. Like each element of the domain has to map to one and only one thing in the codomain. That's a pretty, harsh restriction. But with relations, we don't really have anything. It just has to be a subset. That's it. Okay. So I'm going to pass the row sheet. So initial your name, hopefully the third time on the same row. Okay. Thank you. But this is it, okay? So here we have relations. So the first thing I want to do is to show you an example of an actual relation. So let's go to mouse pad. Okay. There we go. And let's just say that X is the set of 1, 2, and 3. Okay. So we can now define the relation. So the relation, just has to be a subset. Now it can be the actual X Cartesian product with X. Okay, that's perfectly okay. But that relation is not going to be very helpful. Okay, but you can if that is the case. So XR can be 1, 1, 2, 2, 3, 3, and then we look at 1, 2, 1, 3. 2, 1, 2, 3, 3, 1, and 3, 2. This is a relation. But you say, but that's exactly X Cartesian product with X. And you would be right. Because remember, a set is a subset of itself. So R can be X Cartesian product with itself. That's perfectly okay as a relation. Okay? So I'm just going to write down here is a relation over X. Okay. I can also define another relation that looks kind of awkward. That is also a relation. Because the only requirement is the relation has to be a subset of the Cartesian product of set X with itself. Is an empty set a subset of another set? Always. Okay? An empty set is always a subset of another set. even of itself. Okay, so this is perfectly satisfying the only requirement that it is a subset of the Cartesian product. So it is also a relation, okay, over X. Now you can say, what about this? So that is also a relation over X. So you can see relations are very flexible, okay, as long as R is a subset of the Cartesian product of X and with itself, it's all good. Okay, the only question is it useful? So are we doing okay so far at this point with with examples of what is a relation? Are we good? Okay, all right. So what we'll do next is we'll look at certain properties of relations. So this is a concrete example, and we'll move on to a random example, and then we'll move on. Well, actually I shouldn't move on too fast, okay? So this is just an example. It's kind of random, okay? So what we want to do is look at this particular relation. We have X defined to be A, B, C, and D as elements, and then R is relating A to itself, A to B, B to C, D to D, and then B to A. Don't ask me why, okay? It's just a random example. So the answer of the question is, what is ARB? So ARB is true because we can see that AB is a two tuple in the set, which basically means A relates to B. Now the relation only goes one way, okay? So A relates to B, B relates to A, but that's only BA is also a two tuple in this particular case. But when you look at BC, B relates to C, that's true. But C relates to B is false because CB as a two tuple is absent from R in this case. So are we doing okay so far? Because in a two tuple, ordering does matter. BC is not considered the same thing as CB. Are we still good so far? Okay. So you can say ARB is true. You can say BC as a two tuple is in the set R is also true. BRB is false because there's no relation here or no two tuple to relate B to itself. DC as a two tuple is an element of R is also false because we're just basically switching around and say, do we want to look at a relation as a set or do we want to look at a relation as quote unquote a relation? So it's just a notation difference. The meanings are really the same. So do we have any questions about these four examples of whether an expression is true or false? No questions? Okay, all right. So this particular paragraph touches on how we can represent a set in this case. So it's really just an implementation kind of thing. So in this case, because the set has 4 elements in it, so that means we have a matrix 4 by 4 that can be used to represent each entry of a relation. So kind of imagine that you have 4 rows and 4 columns, A, B, C, D as columns, and then A, B, C, D as rows. So we can say it is column relates to row, okay? So when you put an X in a particular cell, it simply means that yes, it does relate, and the absence of an X means they do not relate. So there are 16 unique entries in this particular case. So with 16 unique entries, we can actually represent that entire relation using a 16-bit number. It's called a bit mapped method to represent the absence or the presence of something in a set. So later on in this class, we'll look into implementation, how do we represent a set in programming. There are very general ways to do it, and then there are more specific ways to do it that are far more optimal compared to the general methods. So we'll look into those later on, but right now we don't need to look into implementation yet. Section 5 talks about relations, properties of relations. They're kind of like, injective versus surjective versus bijective to functions, except this time we have different definitions that only apply to relations and not functions. The first one is reflexive. Okay, so we call R defined a relation R that is defined over a set X is reflexive if and only if the following is true. So what we'll do is we'll take a look at this expression here, and then we ask, okay, what exactly does it mean? What is it saying? So the first thing we say is, okay, there's a for all here. So that means, whatever is in the parentheses has to be true for every single element in X. Are we good so far? Okay, it's not a there exists, this is for all. So if you want to check, if you want to programmatically check whether a relation is reflexive or not, you will need a loop, okay? And in the loop, you have to say, okay, for each iteration, we'll assume a particular value, or we'll pick a particular element to be E, and then we check whether EE as a two-tuple is in R or not. Now, if it fails 1, okay, then you can just exit the loop right away, because it wants this condition to be true for every element. So if you find one single element in X such that EE is not in R, then it is not reflexive. R as a relation is not reflexive. Are we good so far? Yeah? Okay. So do you think we can have additional entries in a relation and still be reflexive according to this definition? So let's go back and look at an example, okay? So I'm going to go back to here, and then we'll say, okay, this is a relation. I'm still using X as 1, 2, and 3. So this is a relation, okay? We got 1, 1, and 2, 2. Is this relation reflexive? I'm still using X, as a set that has 1, 2, and 3. So the question is this particular relation R, which only has 2 elements, 1, 1, and 2, 2, is it reflexive?
No.
It is not reflexive because it is missing 3, 3, okay? So we say this is not a reflexive relation over the same set X that we have been using, okay? So now we go, okay, we know how to fix that problem. Okay, so we'll fix that problem. And we look at this one. What about this one? Is it reflexive?
Yes.
Okay. Is a reflexive relation over X. Okay. What about this one? Okay, I'm gonna be a little bit lazy over here. And this time we have one more thing here. So the question is it reflexive?
Yes.
Okay, we got some people saying yes. Does anyone want to say no? Okay.
I think I want to say no because as the definition describes it, it has to be E as an element of R, not E in some other element.
But does it say that if you have E and something else, that it is not reflexive? It does not. So this is actually still reflexive. So this is important because it has to do with how we interpret the expression that we just saw a little bit earlier. It is still highlighted here. Because this expression only says that if EE for every single E in X, if EE as a two-tuple is in R, that that relation is reflexive. It doesn't say a single thing about what if we have E, F, and they are not the same in R. It doesn't say a single thing. Is that okay? It does not say that for every relation or for every element in R, it has to be in the format of EE. That is not what it's saying. It is simply saying for every element in X, we want EE to be in R.
Okay, so as long as that condition is met, it doesn't matter how many more extra.
Correct.
there are. Okay.
Yes. So basically, X Cartesian product with X is automatically reflexive because it contains all the EE entries in it. All right. So do we have any other questions about reflexive, whether a relation is reflexive or not? Okay, all right, let's move on. So reflexive is kind of simple or easy to understand. Symmetric is kind of simple, but not really as simple. So we'll look at the definition of a symmetric relation first, and then we'll go through some examples and ask, well, are they reflexive or not? Okay, so we'll focus on the definition of what is symmetric in a relation. So I'm going to read this out. So it says, pick two elements in X. Now they can be the same, they can be different, I don't really care. Okay, so all you have to do is to say, okay, this thing is in X, this thing is also in X. But you have to remember to pair up every single way, of EF in X. Okay, so it's a double loop if you want to implement it in C or C++ or any programming language. So because you need one loop for E, and then for every value of E, you need another loop to pick F out of X. And they can be the same, they don't have to be the same, so it's a fairly easy, straight, loop, two loops here. So the expression inside is the one that is kind of difficult or can be tricky to interpret. So what it says here is EF is in R if and only if FE is in R. If that expression is true for every way you can choose E and F in R, in X, then R as a relation is known to be symmetric. Are we good so far? Okay? So the first thing we need to do is to remember what is if and only if. Okay? What makes a if and only if true? Okay? So I'm going to go back to Notepad here, and we'll just say, okay, here's X. Well, you shouldn't use X. I'm trying to, okay, we can use D and E. Okay, so D is, so we have D, E, and then we have D if and only if E. Oops. D if and only if E. There we go. So IFF is usually what people use to represent if and only if. Okay, so instead of IF, it is IFF, that stands for if and only if. Okay, so D is just some kind of expression that is Boolean, so it can be true or false. So it can be false, can be true. While D is false, E can be false or true. When D is true, E can be false or true as well. Okay, so we set up a truth table. So the definition of if and only if is if the two sides are the same, if D and E are the same, then if and only if itself is true. If they are different, then if and only if is false. And once again, if they're the same, if and only if itself is true. Okay, this is a review. Okay, we have talked about if and only if already, I think in week 1. Okay, so if you look at this and go like, oh, this looks kind of foreign to me, well, it's time to do some studying because this is a very important concept for the rest of this class. Okay, so now that we know how we define if and only if, and then we look at that expression again. Okay, so you have the truth table on the right hand side, you have the expression in question to the left hand side, then you go, okay, what if EF is not an element of R? And I would like R to be symmetric, so what should happen to the other side? It should be false as well. Okay, so if EF is not in R, you better make sure FE is also not in R if you want R to be symmetric. Okay, what if EF is in R? Well, you better make sure that FE is also in R. So it's basically saying if one exists and then the other also exists, then it's good. Okay, but if one exists but the other one does not exist, then it's not good. Okay, if you find one single case of one is in R and one is not in R, then the relation is not symmetric. So are we okay with that definition for now? Yes? Okay. So now we'll go back to look at some example here. So we'll start to look at this one here. Okay, so we'll start to look at the full set. Okay, so we know this is reflexive. It is also symmetric. It is also symmetric because we know this is, oops, sorry, I have to pull it back a little bit. So if your relation is the actual Cartesian product of x and itself, then we know it is both reflexive and symmetric because it contains everything. Okay? So are we good so far? We're going to skip the empty set for now, but we'll get back to it. What about this one? Okay, we know this one is a symmetric, right? Oh, we know it is reflexive, okay? We know this is kind of like the minimum reflexive relation over R because we need 1, 1, 2, 2, and 3, 3 in it, okay? It's the same as this one. I'm just repeating myself here. But the question is it symmetric?
Yes.
It is also symmetric because, hey, 1, 1 is here. We better make sure 1, 1 is also here. Wait, it's the same thing. It's kind of redundant, but it's okay. It's okay to be redundant. If we pick E to be 1 and we pick F to be 1, then EF is in R, if and only if FE in this R is true, okay? Because it's really the same element. Are we doing okay so far with that? Then what about 1, 2? I see 1, 2 is not in R in this case. It's okay, because 3, 2 is not in R either. Is that okay? So we just don't want it to be like one is there, but the other one is not, okay? So now we look at this one, okay? It is not reflexive, but is it symmetric? It is symmetric, okay? It is not reflexive, but it is symmetric. And I'm gonna add symmetric to this one. And this one we talked about already, so this is redundant. I'm gonna remove it because it's really the same thing as the row before. What about this one? It is reflexive, but is it symmetric? Not symmetric, okay? So we say it is not symmetric, we do not say it is asymmetric, because asymmetric has a different meaning when it comes to characterizing a relation. So not symmetric is just saying that it is not symmetric. Asymmetric has a different meaning. Okay, cool. So now we go back to the empty set, okay? So the empty set, is it reflexive? Is it reflexive? Not symmetric. So we're going back a little bit to look at reflexive, the reflexive definition first. It is not reflexive because if I choose a particular element in X, like 1, 1, 1 is not in R, right? So it is not symmetric. It's not reflexive, sorry. It's not reflexive, but is it symmetric? So now we have that really tricky question. The relation is empty, nothing relates to anything, but is it symmetric?
Yes.
It is symmetric, very good. So the question is, if there's nothing on this side of the mirror, and you look into the mirror, and the other side also has nothing, is the mirror doing its job? Yes. That's kind of the deal, okay? And then you ask, how can there be nothing on this side of the mirror when the mirror cannot see anything? Well, if you do any type of Unity or game programming, you would understand that, because you can have a point of view in the game that does not correspond to an actual object. So there's nothing to see. You're just basically looking at something from a particular angle when you're not really there. Okay, so that is kind of interesting because the empty set is actually symmetric. It's not reflexive, but it is symmetric. So are we good so far with the definition of symmetry? Symmetry simply says if AB is in, then BA should be in as well. If AB is absent, then BA should be absent as well. Okay, you cannot have one without the other. They can both be missing. All right, so we are now moving on to transitive. Transitive is actually, it looks kind of ugly, but it's not really as ugly as it is, okay? Because we actually we understand transitive relations fairly well, because in real life there are a lot of transitive relations. So with transitive relations, we have to have a triple loop. So we have E to go through every single element of X. We have F to go through every single element of X. And then we have G to go through every single element of X. So we have 3 loops in this case, okay? The first question you need to ask is EF in R, okay? And if the answer is yes, okay, then you have a lot more things to consider. So we'll be lazy and look at the case when EF is not in R, okay? You go through the triple loop. At the innermost part of the triple loop, you first ask, well, I just want to be lazy. Is EF missing from R? If the answer is yes to that, EF is not in R, you can just say, oh, this entire expression is true. Let me highlight what I mean when I said the entire expression. So what I say the entire expression, I'm referring to this entire expression. You can go like, wait, hold on a second here. How can a false of EF is in R automatically make this entire thing true? Yes? I think you got the right answer in your head. Yes, go ahead.
Because if it's not, then the left side could be false, and false implies true.
Okay, you got it. So if EF in R is false, the conjunction is false because you only need at least one side of a conjunction to be false for the entire thing to be false, right? So why is it such a great thing when something is false? Because this is an implication. It is not an if and only if. It is just a simple implication. So with an implication and the left-hand side is false, what happens to the value of the implication itself? It is true, okay? I don't even have to bother to see what is on the right-hand side of the implication, because if the left-hand side is true, I just say, okay, the entire implication is true. So I'll be doing okay so far with that, okay? So let's look at scenario 2. Scenario 2 says, yep, EF is in R. Oh, okay, now we have more work, right? So now we look at FG, and we say, well, is FG in R? Once again, if it is not in R, we still have kind of a shorter answer because it is still a part of the conjunction, right? So if EF is in R but FG is not in R, we just say, yep, it's good, right? So now the only long answer that we have to answer is what if EF is in R and FG is also in R? Now remember, F is representing the same value in the same iteration of the innermost part of the loop, okay? So if EF is there, FG is also there, now I really have to check whether EG is in there or not. Because if EG is in, then the implication is true. If EG is absent, then the implication is false. Is that okay? So the only way to make the implication false is to have EF in R, FG in R, but EG is not in R. If you can find me at least one example like that, okay, one combination of EF and G such that that is true, then we know R is not transitive. Are we good so far? Okay, so we're going to go back and take a look at some examples. Okay, and we'll look at the examples that we have already looked at here. So we'll look at this one first. Is this one transitive? It is the entire thing, right? Every single possible two-tuple is here. Wait, did I just say that? Did I just say that every possible two-tuple is here? What does that mean? What does that mean in this new definition? That means, yep, this is guaranteed because R has everything, right? Every single possible two-tuple is there. This one is also going to be there, and this one is also going to be there. So we have true, and true implies true no matter how you choose E, F, and G. And go like, oh, okay, we're good then. Does that make sense? Okay. So we go back to this one and say, well, this one is also transitive. Very good. We look at this one, okay, so this time we're not going to skip and go back to it a little bit later because I think we got a hang of it now, okay? This is an empty set. Nothing is in that particular set. There are no two tuples of any kind in R this kind. And we look at the definition. Oh, doesn't that mean these exist? They all have to be false in this case because there's nothing in the set. So we have false and wait. I think I can answer that question already. The whole implication is true, no matter what you choose, because there's nothing in the set. So EF is in R automatically fails. But if that automatically fails, that means the conjunction is automatically false. If the conjunction is automatically false, the implication is automatically true. Done. Okay, so empty set is interesting because it actually has a lot of properties. When people say, but it's empty, how can they have all of these properties? It has to do with how the properties are defined. Okay, so let's go look at another example here. So this one is transitive. Okay, very good. What about this one? Is it transitive? Okay, so let's think about how we can choose E, F, and G. Okay, so in one particular case, I say E, F, and G are all ones. Okay, so what happens in that case? 1, 1 is in R, and 1, 1 is in R, implies 1, 1 is also in R. Not a problem. Okay, what if E is 1, F is 2, and then G is 3? Okay, then we look at this and go like, hey, 1, 2 is not in here. The whole thing is true automatically. Okay, is that making any sense? Okay, so turns out this relation is also symmetric. We don't have a problem. Oh, transitive, sorry. It's also transitive. And what about this one? What do you think? Kind of the same argument. It is also transitive. Okay, what about this guy here? Okay, we know it's reflexive. It is not symmetric, but is it transitive? So if you compare the last one versus the ones, the two above it, the only difference is this one has got a 1, 3 in it, right? So what can you possibly do with 1, 3? Well, let's think about the cases when 1, 3 is one element is one of the three. Okay, E, F, and G. One is 1, and the other one is 3. Okay. How many ways can you combine it? Can you make it so that the expression is false? So let's think about it. Okay, E is 1, F is 1, and then G is 3. Okay, 1, 1 is in. 1, 3 is in, but 1, 3 is also in. So it's all good. Are we good so far?
Say that again.
Okay, so let me write down here. So we say E is 1, F is 1, and then G is 3. So in this case, we have 1 in X and 1 in X. Okay, so we have true and true. Then we have implies 1. Wait, hold on a second here. No, because we have to look at relations. So we have 1, 1 in R, and then we have 1, 3 in R, and that implies 1, 3 in R. Okay, so on the next row, I'm gonna specify what is E and what is F and what is G. Okay, so this is F, that is G, and this is E, and that is G. Is that okay? So I'm really just substituting values in this case. So can someone tell me whether the implication itself is true or not? It is true. Okay. So as it turns out, in this case, in the last one, it is also transitive. Okay. In order for something not to be transitive, you need to have E, F, G as distinct elements, and then you have a chance of making it not true. Is that okay? Okay. So let me just write down here that this is actually transitive. And what is not transitive then? Well, I can give you a very simple example. 1, 2 is in, and 2, 3 is in. Is not reflexive, right? Not symmetric, and also not transitive. Does that make sense? Well, let's double check. For anything to be reflexive, you need to have elements relating to itself. The only thing in this particular relation is relating an element to something else. So we know it's not reflexive. 2, is it symmetric? Well, I see 1, 2 here, but I don't see 2, 1. So it's not symmetric. The next one is it transitive? No, it is not transitive. Because I can say E equals to 1, F equals to 2, G equals to 3. Then EF is in R is true, FG is in R is also true, but EG is in R is false. So now we have true implies false, which makes the implication itself false. Yep.
So you're just looking for one counterexample?
Yes. Only one counterexample can prove that it is not a particular property because of the for all symbol.
Yeah, right, exactly.
Because the for all symbol, remember, you can apply a negation to the for all. And what happens is you can turn the for all into a there exist, and then you negate whatever is in the parentheses. So you only have to find one counterexample to show that it is not true. Yep.
If that X is done for 1, would you just have to find one that is true?
Yep. All right. So are we okay so far with transitive? Yes? Okay. All right. So then we have antisymmetric. Not asymmetric, it's antisymmetric, so I stand corrected. It's called antisymmetric, but it is antisymmetric does not mean it is not symmetric. So it's a little bit different. Okay. So we look at the definition. Okay, you can see the definition is very similar to something that we have seen before, but it's not exactly the same. It seems to have some elements of being symmetric, but it also has some element of transitive, okay? But it's neither, okay? So we want to be very clear that this is not symmetric nor transitive, okay? So let's double check and see what this is really saying, okay? We have to set up a double loop. E has to go through every single element of X. F has to go through every single element of X, okay? And we want each iteration in the innermost part of the double loop so that the expression inside the parentheses is true for every single iteration. If it's false only once, then it is not antisymmetric. Is that okay? So what are we looking for? Well, the first thing is we're looking for EF in R and FE is in R. If at least one of these two is not true, it's okay. The implication is true. Okay, which is not a concern. Okay, it says okay, we can still assume the relation is antisymmetric. Okay, so the only time a relation is not antisymmetric is for the left-hand side of the implication to be true, but E and F are different. Okay, so that means okay, so let's look at some examples. Okay. So let's take a look at some examples. Can you guys remember this expression, more or less? Okay. Okay, let me see if I can show this at the top and then move my mouse pad below that so that we can see both. There we go. Okay, that works. Okay, so we look at this one first, okay, and we ask, is this antisymmetric? Can you make the expression in the parentheses false? Can you choose E and F so that the stuff inside the parentheses is false? If you can, tell me what E and F you choose. Okay. Go ahead. 3 and 1. Okay, so let's try that. Okay, E is 3 and then F is 1. Okay, so if that is the case, we plug it in to the equation and then we ask, is 3, 1 in R? 3, 1 is in R. Yes. Okay. And then the next question is Fe, which is 1, 3 in R? Yep, 1, 3 is also in R. So now the conjunction is true. Okay. What about the right-hand side of the implication? Does 1 equal to 3? Nope. So we have true implies false, which means the implication is false, which also means this relation is not anti-symmetric. Are we good so far? Okay. So now we write it down here. Okay. Oh, there's this one over here. Not anti-symmetric. There we go. Let's look at the empty set. Okay. So if you look at the empty set, okay, nothing is in the empty set, right? So what does that make the left-hand side of the implication? It has to be false, okay? Because nothing exists in R in this case. So that means the left-hand side of the implication is false, okay? Wait, that means I don't even have to look at the right-hand side, because if the left-hand side of an implication is false, the implication itself is true. Okay, so this means no matter how I choose E and F, the expression inside the parentheses, which is this part here, is always true. Oh, okay. So the empty set is also anti-symmetric. Okay, let's look at this one. Okay, this one says, we got 1, 1, 2, 2, and 3, 3 only. We know it's reflexive, it is symmetric, it is also transitive. The question is it anti-symmetric? Okay, so I think we start to understand that, if the left-hand side of the implication is false, we are good. Okay, so we are looking into cases where the left-hand side is true. Then we have something to think about. Does that make sense? Okay, so we want EF in R and FE to be in R. This time the set is, the relation is non-empty, but the only entries that we got is E and F have to be the same in order for the left-hand side of the implication to be true. Does that make sense? Because we only got 3 elements in this relation, 1, 1, 2, 2, and 3, 3. So E and F have to be exactly the same thing in order for the conjunction to the left-hand side of the implication to be true. So that means E and F are the same. If EF is in R and FE is in R, it does imply E and F are the same in this case. So it is antisymmetric. Okay, so let's look at this one. Okay, is this one antisymmetric? Same thing, for the same reason, it is antisymmetric. So it is also antisymmetric. What about this one? Now this one is transitive, but the question is, can I find E and F so that the expression inside the parentheses is false? How would you choose E and F to make it false? 1 and 3? Okay. Well, if you choose E to be 1 and F to be 3, then we say 1, 3 is in R. Okay, that's all good. What about 3, 1? 3, 1 is not in R. So that means the conjunction is false, which also means the implication is true. So we cannot make it not antisymmetric. So this one is still antisymmetric. What about this one? This one is not transitive, but is it antisymmetric or not? So once again, you have to focus on finding an E and an F so that EF is in R and FE is in R, and we cannot find such a case, right? Because it is 1, 2 is in R, but 2, 1 is not. Okay, so, okay. What about 2, 3? 2, 3 is in R, but 3, 2 is not in R. So this one is also anti-symmetric. Okay. So what is the easiest way to make something that is not anti-symmetric? Because it looks like we got more. Most things are anti-symmetric. So this one is easy. Okay, let's go through every single one, okay? We know this one is not reflexive.
You're off screen for us.
Oh, sorry about that. There we go. So we know this one is not reflexive. Is it symmetric? Yep, okay, it is symmetric. Is it transitive? It is transitive. Okay, but what about anti-symmetric? Not anti-symmetric. So do we have any questions about this latest example? Are there any questions about why it is not reflexive? It's missing 1, 1, 2, 2, and 3, 3. Okay, so it's not it's not reflexive. It is symmetric because if AB is in it, and then BA is also in it. Okay, so we have 1, 2, and 2, 1, and then for everything else, it's absent. So it is symmetric. It is transitive because there's no way for me to construct a case where we have EFG so that EF is in the set. Oh, actually, I stand corrected. This one is not transitive. Okay, so how do we construct a not transitive case? How do we prove it not to be transitive? Okay, yep. Okay, so if we say it's not transitive, we have to pick E, F, and G. Yep, go ahead.
1 maps to 2, 2 maps to 1, 1 maps to 1, so E would be 1, F would be 2, and G would be
1 again. Yep. In that particular case, 1, 2 is in R, right? 2, 1 is also in R, but 1, 1 is not. So that's why it is not transitive. Okay, I missed it the first time. Yep.
I have a question. So, in the definition for like symmetric and all of it, it says for all EFG and EFG or EF.
E and F. Yep.
Doesn't that mean that we also need to have at least like a 3 in there for it to be symmetric?
In order for this to be okay, remember the MT relation is symmetric.
Okay, great.
So it is not transitive, but it is also not anti-symmetric because in order for that proof, okay, not anti-symmetric, because all we have to do is to pick E as 1, F as 2. Because EF is in R, right? FE is in R, but yet E and F do not equal. They're not the same. Are we good so far? Yeah? All right. So the properties of a relation really just kind of boils down to the evaluation of these expressions. Okay, so that means you really have to start to get used to the for all quantifier as well as the Boolean operators like conjunction. I think all of you got it already, but implication and if and only if are the slightly more tricky ones because we usually do not consider those as operators in C and C++, but in this class we do. Okay, but then the next question is, okay, so now that we know the definitions of reflexive, symmetric, transitive, and anti-symmetric, what are we going to do with these? I mean, how are these useful? Okay, so when I teach this class, I try my best to relate it to something that is actually, important or actually, practical. So the next thing we want to talk about is the definition of partial ordering. So partial ordering is easy, okay, because all it says is it has to be these 3, okay. So in order for relation R to be a partial ordering relation, it has to be reflexive, it has to be antisymmetric, and it has to be transitive. We don't care whether it's symmetric or not. It may be, it may not be, okay, but we don't care. Is that okay? This is partial ordering. So partial ordering means in R may not be defined for certain pairs of elements of X. So, okay, so let's check out an example like this, okay? That is a partial ordering. So let's go back here. All right, so, well, of all the ones that we have seen already, let's see which one is partial ordering. Okay. I'm just going to change the size of my mouse pad so I don't forget to scroll up a little bit later. Okay. So let's take a look at this one first. Okay, we have already figured out its properties. So we are only checking to see if it meets all the requirements here. And go like, nope, does not meet all the requirement because this one is not antisymmetric. So it's definitely not partial ordering. Okay, so let's move on to the next one. Let's look at this one. Is this one a partial ordering relation? The answer is no, it is not reflexive. Okay, it has to be reflexive. It has got everything else, but it's not reflexive. And we look at this one. It is reflexive. Okay, cool. It is antisymmetric. Cool. And it is also transitive. Yes. Okay, so we found one that is a partial ordering relation over the set of 1, 2, and 3. All it is saying is we know how 1 relates to 1, we know how 2 relates to 2, we know how 3 relates to 3, but we don't know whether 1 relates to 2, whether 3 relates to 1, and so on. So it's partial, okay? And let's look at this one here. Is this one a partial order? Well, since it's not reflexive, forget it, it's not, okay? Let's look at this one here. Is it a partial order? It is reflexive, great. It is transitive, great. It is antisymmetric, great. So this one is indeed partial order. Are we good so far? Okay. And I think we got one last one. Yep. Oh, we got 2 more. What about this one? Is it a partial order? It is not reflexive, forget it. What about this one? It is also not reflexive, forget it. Are we good so far? But what does it mean when we have partial order? Because I think most of you know what ordering is, right? When you have to express a sorting algorithm, you have to express what is the actual outcome, okay? Is it going to be in increasing order, decreasing order, non-decreasing, or non-increasing, okay? So that ordering is usually, totally order. I mean, it's not partial, okay? So the question is, so this is, I'm giving you an example in real life, something that has a partially ordered relation, but it's not full. This is coming from a beer commercial, from way back when. Okay, I think it's an Australian beer, and it shows like 2 actors. Okay, one actor would do something that is smooth but not rich, and then the other actor would do something that reflects rich but not smooth. Okay, so we'll basically say, we'll make the assumption, okay? Of course, this is like a very general assumption that smooth and rich is more desirable than smooth but not rich. Smooth and rich is also more desirable than not smooth but rich. Smooth and rich is more desirable than not smooth and not rich. So we're basically defining some relation here, okay? But more desirable is definitely not, it's not reflexive. Does it make sense? Because it doesn't relate to itself. Okay, so in order to make it reflexive, it's easy, because instead of using more desirable than as our relation, then we'll say at least as desirable as, as a relation. So this way it is reflexive, because not rich and smooth is at least as desirable as not rich and smooth. Does that make sense? Yes? Okay. So now we can now say, and I'm going to abbreviate that at least as desirable as ALADA. Yes, so now you have a new term today, as ALADA. Okay. ALADA. Now, if anyone wants to turn it into a meme, that's fine. Okay, I don't have a problem with that. Okay, so now we can use ALADA and say smooth and rich is ALADA smooth and rich. Okay, that kind of makes sense, right? Smooth and rich is ALADA smooth but not rich, because it's missing one property that most people think is desirable. Is that okay? All right, so I define all of this stuff here, and then we look at this as a relation, and then we ask, is ALADA as a relation, is it reflexive? Well, let's check. Okay, reflexive means each label relates to itself. Is that true? Does every label relate to itself? Yep. Okay. Is it transitive? How do we know it is transitive? I'll show you an example that shows that it is transitive. Smooth and rich is ALADA smooth. Let's pick one that is a little bit more fun. Smooth and rich is ALADA rich, smooth but not rich. Okay, there we go. So smooth and rich is ALADA smooth but not rich. Is that okay? Then we focus on smooth but not rich and see what it relates to. Okay? So smooth but not rich is ALADA not smooth and not rich. Okay? Kind of makes sense, right? Now the question is smooth and rich ALADA not smooth and not rich? The answer is yes. Okay, we see it right above here. So it is transitive. So this relation is a partial order. Now, why do we call it partial? Because we cannot actually relate. We cannot see which one is more desirable, or whether they are even at least as desirable as each other. Not smooth and rich does not relate to smooth but not rich in any way. So between those two labels, we don't know the ordering. Is that okay? Does it make sense? So if you will excuse my, kind of cliche example, okay? So if this is in a dating site, okay? If ALADA is a ranking that people use in a dating site, okay? Okay, we can see that, right? And it only has these labels. There are only 4 labels, okay? Then we have a problem because there's no way to sort the list. If you have a whole bunch of people who are smooth but not rich, and another bunch of people who are, what did I say earlier? Smooth but not rich, and then you have another bunch of people who are not smooth but rich, okay? Then there's no way to order these people anymore, because between those two labels, there's no definition. ALADA is not defined between those two labels. Are we okay so far with this? So this is a relation that is just partial ordering. Okay. Are we good? Okay. So the next topic is total ordering. And I think you probably saw this coming, because if there's a partial, there's probably a total or complete or something that is not partial, right? So total ordering is actually pretty easy to define as well, because the first 3 requirements are the same as partial. So that means everything that is totally ordered is also partially ordered. That kind of makes sense, right? Okay, but what is the extra requirement here? The extra requirement is called comparable over X. What does that mean? That means no matter how you choose two things in X, okay, one of these two has to exist. Are we good? So once again, we set up a double loop. Outer loop goes through every single thing in X, as E. Inner loop has a variable f that goes through everything in X. Okay? In the inner loop, then you look at the disjunction and you say, is the disjunction true? Well, the disjunction is true if at least you have ERF or FRE. The only time the disjunction is false is when both are missing. Is that okay? So when you look at this, what does it mean in English? Okay, because remember, my own advisor in graduate school said, what? Tech, use English in your dissertation. Okay, so I can understand. So what does it mean in English? In English, all that means is every element has to relate to other elements. Has to relate to every other element in some way. Okay? That's all it's saying. So now we cannot have the situation that we had before. Because in the situation that we had before, between smooth and rich, we have two labels that do not relate in any way. So we have to make sure that this requirement is also satisfied in order for a relation to be total ordered. Okay? So in terms of programming, okay, why do we care about something being partially ordered or totally ordered? Okay? Now remember, everything that is totally ordered is automatically partially ordered, but we can have relations that are partially ordered but not totally ordered. Okay? So let's think about game stats. Okay? So let's say you're the one running a game website and you want to produce a ranking of all the players for this week. So what factors would you use to rank the players? How many games they played? How many games they won? The win to lose ratios, rating by other players. Are they awful? Are they really good teammates, and so on? How much money did they spend, right? To buy skins and whatnot. Okay, because that's kind of important. Okay, to generate revenue. So you have all of these numbers, to help you evaluate, a particular player. Are we good so far? Okay. So now you have, let's say, 4 numbers, okay, 4 individual numbers for each player. And you have to define a function that returns true if and only if one player should be ranked higher than the other player, or at least as good as the other player. Okay, that's the key. Okay. Are we good so far? So I'm just going to write it down here. Okay. So we are looking at a subroutine where you say is ranks as high at least as high as. Okay. So that's kind of the relation name of the subroutine. And then you have, player P1, player P2. Okay, and we can pass these by reference and probably const because when you're comparing, you probably should not be modifying the objects. Okay, so now you're defining this subroutine in C, C++, or other programming language that does exactly the same thing. Okay, this is a relation. Okay, if this is a relation, what is our set X? Okay, this relation is defined over what? It's defined the set of all players. Okay, so you look at all the players, maybe for this week, maybe for the year, but you have confined to a set of players. Okay, then why is it a relation? Because it returns a Boolean. It tells us whether a particular player P1 is ranking at least as high as another player P2. Are we good so far? Now you can see that it's at least as high as, which means it is by implication, reflexive. Because the same player, it kind of makes sense that if P1 and P2 are exactly the same object, that this function should return true, because it's the same player, and don't tell me a particular player is not going to rank at least as high as himself or herself. So it makes sense, right? But now the question is it transitive? So if a player is known to be at least ranking as high as, okay, I'll use 3 different players. If player 1 is ranked at least as high as player 2, and player 2 is ranked at least as high as player 3, does that make sense that player 1 should rank at least as high as player 3? So you have to make the logic of the subroutine to satisfy that requirement in order for this to make sense. Okay? But the question now is not about whether it is partially ordered. It is about why does it have to be totally ordered. Okay? So there are many ways to make this partially ordered. That's pretty easy to do. But to make it totally ordered is not always that easy. But what is the bottom line? If I make this partially ordered but not totally ordered, what is a potential problem? Because remember, what your job is to pop up a list and rate the players and say this is our top player, this is the second, this is the third, and so on. So what happens when this is not totally ordered? You may not be able to produce such a list. You cannot sort without a totally ordered relation. Is that making sense? Is that making sense? Okay. Okay. So how can we make something like that? Okay. So I can give you, some pseudocode here that kind of give you an idea of how to make a function partially ordered but not totally ordered. Okay. So you can say if p1 dot KDS is, let's see, we want it to be at least as high as, so the KDS has to be greater than or equal to p2.kds, and we return true. Okay, and if that is false, then we look at something else. Okay, so we look at something else. KDS is a kill-death ratio. Oh, KDR. There we go. Okay, what else do you want to use for ranking players? Time in game. Okay, we want people to spend their entire day in game, right? Time in game. Okay, and then we say, okay, if these two are less than, if they're less than in both cases, then we look at how much money they have spent. Okay, so in-game purchase. And if all of these fail, we return false. Okay. So now when you look at this, you ask, is it reflexive? If I pass the same player as P1 and P2 into this particular subroutine, what is it going to return? It's going to return for true. True for sure, right? Okay, all right. Is it transitive? Now that is tricky, okay? I don't think this is necessarily transitive, because one player can be better than, and at least as good as the other player using one criteria, and then the second player can be better than the third player using another criteria. The first player may not, let's see, would that work? Well, can someone think of an example where you have 3 players with the stats and we prove that this is not transitive? Can we come up with an example like that? Okay, so we'll create a few objects. Okay, so we say this is object A. So object A has KDR E being 5 and TIG being 2 and then IGP being 6. Okay. We have player 2, we have player B. So player B has KDR being 4, TIG being 3, and IGP being 7. And then we have player C. Player C has KDR being, let's see, 6, okay. And then it has TIG being 2, and then IGP being 7. Okay. So in this case, is the relation transitive? If I just look at these 3 players. So A versus B, okay? If A is P1 and B is P2, is the relation going to return, is the function returning true or not? It's going to return true. What about B versus B versus C? So if you look at B versus C, KDR is not greater than or equal to. We drop to the second line, and TIG is greater than or equal to. So it's going to be returning true for B versus C. So now we have to look at A versus C. So we have to look at this versus this. So you can see in this case that it will still return true. The question is, can I engineer this case so that it returns false when I compare A versus C? Any idea? Okay. So it's still greater than or equal to, right? Well, we can make this 4, then we can make this 3. So in this case, 5. Yeah, so in this case, it is not transitive anymore. Is that okay? Now, if this is not transitive, if I can find one case where this ranking function is not even transitive, that means the relation is also automatically not partially ordered. Is that okay? Now, if it's not partially ordered, but you did not know that it is not even partially ordered, and then you supply this function to quicksort or some other sorting algorithm and say, okay, this is how we define the relationship between two things in the sorted order. What do you think is going to happen when you publish the list of players and their ranking at the end of the week? I think no one's going to play your game anymore. Because people would then be asking, so how do you do this ranking? And go like, oh, this is how we do the ranking. And then they will go, but it doesn't make sense. Because it's not even partially ordering. It fails the simple test of whether it's transitive or not. If A is at least, it should be ranked as high as B, and B is ranking at least as high as C, A can end up ranking lower than C. What is going on? You cannot sort using a comparison like that. Is that okay? So this is why the concept that we have learned so far is important. Because if you want to sort something, and then also your sorting function is not something simple like, oh, we're just comparing two numbers, okay? Instead, you have some kind of complex logic in your comparison. Then you have to evaluate, is it reflexive? Is it transitive? Is it antisymmetric? Because if it's not, then it is not even partially ordered. If it is partially ordered, then you have to ask one additional question. Does it define a relation between every two elements, one way or the other way? If the answer to that question is yes, then you have a total order. If the answer to that question is no, then you still have a partial order, but you cannot use it for sorting, because for sorting you need total order. All right? So on Wednesday we have our exam, so don't forget to come here on time, because I will start the exam on time, And also don't forget that it is open book and open notes. So bring your stuff with you, for the exam. I'll see you guys on Wednesday. I do have office hours after today's class and also tomorrow from 9:30 to 10:30.